Okay guys, so next step, we've done momentum, let's have a look at energy. Energy considerations in special relativity lead to a lot of interesting things like a better understanding of particle physics or conservation of energy in a much more complicated setting than we've seen before. So let's start with good old-fashioned kinetic energy, right? The regular kinetic energy is 1/2 mv squared, and what we're going to do is we're going to derive an expression for the relativistic version of the kinetic energy. It's a bit of a slog, but it's fascinating to see it go through from one step to the other. So one way to start is to say that the change in kinetic energy is due to work. Okay, so let's see. For work, I'm going to do the general definition of work in one dimension. It's the integral of the force. You might remember work can be F dot displacement, or it can be the integral of the force over a displacement. So what I'm going to do now is I'm going to use that V is equal to dx dt, right? Or I can rewrite that as dx is equal to v dt. So I'm going to replace that dx with v dt. So now we end up with, the integral of force times v dt. Next, I'm going to use the Newton's second law, right? So there's two ways to write it. You can write it F equals ma, or, and this is more useful for us in this case, F is equal to dp dt. It's the time derivative of momentum. So let's replace F with that. And so now we end up with the integral of dp dt times v dt. So we see here that the dt's are going to cancel, and let's rearrange everything here, and we end up with the integral of v dp. Now let's use relativistic momentum, right? So we're going to use that momentum is equal to gamma mv. So this now becomes the integral of v with respect to, now what does this all mean? Gamma mv. So this is getting a little tricky. So the m is something that we can pull out because that's just a constant. What I'm going to use here is I'm going to use integration by parts. If you remember integration by parts, that basically says that the integral of a, or one way to write it is the integral of a db is equal to ab minus the integral of b dA. So that's one way you can write it. And when we apply that to this, if I integrate that by parts, here I get m. Nope, that's right. I get what do I get? I get v times m gamma v minus the integral of, so then I'm going to do integral of that with respect to that. That's sort of what happens when you do integration by parts. So I end up with m gamma v dv. Okay, so I end up switching it around, and let me do a little simplification here. So I end up with m gamma v squared as my first term, and I'm going to factor out that m minus m, the integral of gamma v dv. All right, we are having fun now. I'd like to rewrite that v dv because this is a complicated integral, right? There's a v inside this gamma. So what I'm going to do is I'm going to use dv squared dv is equal to 2v, right? And I can rearrange that to say that dv squared over 2 is equal to v dv, right? See how that works out? So now I have I can replace that v dv with this dv squared over 2. So this here, the first term is still m gamma v squared minus, and then I'm going to plug in, so I still have that m in there. So I'm going to replace that v dv with 1/2 dv squared. And I'm going to replace that gamma. Let's put that gamma in there too. Remember, gamma is 1 over the square root of 1 minus v over c squared. So this is something integrable. You can look this up in a table, right? That's not too bad to do. So if I look that up in a table and I evaluate it, I end up with, so I still have my first term here, gamma v squared minus, and I'm pull out that 1/2, and that integrates to minus 2 c squared square root of 1 minus v over c squared plus some integration constant. I just, well, you don't even need that in a table of integrals. You can just sort of see it's an integral of a rational. That's a lot of ways you can do it. Let me multiply it out. I know this is getting crazy, but it's all for a good cause. Gamma v squared minus, let's see. No, I had 2 minuses before, so it becomes a plus. mc squared times the square root of 1 minus v over c squared. And then minus, I'm going to call, we multiply this m over 2 times c. I'm just going to call that a new constant. We're going to call it E naught. We'll see why later on. That'll come in handy later on. Let me do a little factorization. I'm going to factor out m gamma from this whole thing, so I end up with m gamma, and then v squared, let's see, plus a little lost there. Okay, I see it. So I'm just going to factor out the gamma. Remember, this is 1 over gamma here, right? So when I factor out the gamma from here and I factor it out from there, I end up with a 1 over gamma squared. So this ends up being c squared over gamma squared. Okay, I see where I went here. All right, so what do you want here? So just remembering what gamma is again, remember that gamma is 1 over the square root of 1 minus v over c squared. So I'm going to plug that into here. All right, and so this ends up becoming here m gamma v squared plus, and then it's c squared times 1 minus v squared over c squared, because that's a gamma squared, like so, minus epsilon naught. And you notice that this v squared will cancel out this minus v squared, because that c cancels out that c. And what do I end up with? I end up with m gamma c squared minus epsilon naught. So that's our sort of kinetic energy here. Okay, so this is step 1, is we get this kinetic energy is equal to m gamma c squared minus E naught. So that's weird. We're not done yet. We've got step 1 going here, but what do we want to do next? Well, we're going to make a requirement. What should the kinetic energy of a particle be when it's at rest? Well, when it's at rest, we expect its kinetic energy to be 0, right? So let's bring it up here. I'm going to go back up here. So we're going to require that the kinetic energy is 0 at v equals 0. That seems like a reasonable thing, right? That kinetic energy at v equals 0 is equal to 0. That seems like something we should ask. So let's plug it in. So we're going to say that the kinetic energy is 0 when m and gamma at v equals 0 is 1 c squared minus epsilon naught. So I solve that for epsilon naught. So that means not epsilon naught, E naught. E naught is mc squared. Ooh, that's interesting. So in order for the kinetic energy to be 0 at when it's not moving, that has to be true. But what is that thing? Well, we're going to see in a second. So this leads to the kinetic energy is equal to m gamma c squared minus mc squared, or the way it's most often written is that kinetic energy is equal to mc squared times gamma minus 1. There. So here we have an expression for the relativistic kinetic energy. It's kind of cool. It's got that mc squared. We've seen that thing in there before, right? So what can we do with that? Well, let's unpack a little more of this whole situation. I'm going to, just for interest's sake, let's look at the Taylor expansion of gamma. Look at the gamma expansion, and you'll see why. This doesn't look at all like a half mv squared, right? But let's think about when I were to do a Taylor expansion or a Maclaurin series of gamma. You know, gamma is exactly 1 over the square root of 1 minus beta squared, right? But if I Taylor expand it, you can show that it's 1 plus beta squared over 2 plus 3 beta to the 4th over 8 plus blah 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 blah, right? In the case, for the situation, for when we're going slow, so when v is much, much less than c, then we can approximate gamma as approximately 1 plus beta squared over 2. Because if gamma is much, if v is much less than c, this is c and this is v, then this is going to be a really, really small number compared to this. So let's keep the first two terms there. And if I were to plug this, let's call this equation, let's call this equation 1, right? If I were to plug this into 1, plug it into 1, and simplify, and I'll leave that as an order, you can show that kinetic energy is approximately 1/2 mv squared. So it looks like a weird expression for kinetic energy, but it turns out to be, simplify down to the kinetic energy that we're familiar with in everyday life. So that's always a useful thing when our theory for high-speed motion properly reduces to the everyday experience of kinetic energy. What a derivation. How much fun was that? Well, let's look at some sort of what happens because of this. So real quick, here's the kinetic energy. It's mc squared times gamma minus 1. So if you're to plot kinetic energy versus speed, classically the kinetic energy just increases as v squared, right? The kinetic energy goes to infinity as the speed approaches infinity. But in relativity, the kinetic energy tends towards infinity as you approach the speed of light. In other words, to get to the speed of light, you would need an infinite amount of energy, right? Which is not readily available. So it is impossible to get something with mass to the speed of light because the amount of kinetic energy it would require would be infinite, which is a lot. How about, do I have this? Nope. What if I have a baseball with a mass here? So say I have a baseball that has a mass of 0.145 kilogram. Oh, no. That's something I want to do later on. First, we have this kinetic energy is equal to mc squared times gamma minus 1. So what am I going to do with that? Well, let's multiply it out. So there's the two terms. And I'm going to rearrange it a little bit. So we have gamma mc squared on the left, mc squared, and then the kinetic energy term. And I'm going to call this left-hand side total energy E. I'm going to call this thing here mc squared the rest energy, and then the kinetic energy will be that extra term. So in other words, we're saying the total energy of a particle is equal to the kinetic energy plus some new kind of energy. If it's at rest, it still has some energy, it turns out. This mc squared term here, it's not kinetic energy, but it's an energy just from the fact that it exists, which is not a classical thing, but we're going to call that the rest energy of it. It's basically a particle at rest has some inherent energy. We call it the rest energy, and it's mc squared. So you may have seen E equals mc squared before, and that's that expression. The total energy of the particle, if it's moving, will be gamma mc squared. So it's a sum of the rest energy plus the kinetic energy. Now, I just sort of waved my hands and argued for the rest energy here, but Now, Einstein's complete derivation of it is a little bit beyond the scope of this course, but basically it's an equivalency between mass and energy. He's saying that the total energy of that the mass of an object has an equivalent energy. And it turns out it can be converted into energy, and the energy can be turned into a mass. There's a relationship between the mass of something and energy, and that relationship is proportional to the speed of light squared. So here's what I was getting at before, right? If a baseball has a mass of 0.145 kilograms, what is its equivalent energy? Well, you just use equals mc squared, right? So you would do 0.145 kilograms times the speed of light squared, so about 3.00 times 10 to the 8 meters per second squared, and that works out to approximately 1.305 times 10 to the 16 joules. That's a lot of energy. If you could somehow convert a baseball into pure energy, it would be a lot of energy. Turns out the world consumes about 5.6 times 10 to the 20 joules per year. I just made a rough approximation. That may be off by a couple orders of magnitude, but just as a rough guess. And just by the way, comparing that to a baseball, you could power the world with, I guess, 10,000 baseballs if you could turn them all into energy. But which comes out to, so that's how much energy the world consumes per year, roughly. That's, people, electrical energy, industry, all that stuff. Which comes out to about burning 1.3 times 10 to the 13 kilograms of oil per year if we got all our energy from burning oil. So that's just roughly how much it is. So how much mass would you need to make that much energy? So I could use the E equals mc squared to do that, right? So how much mass would I need to convert to energy to power the entire world for a year? So it would be 5.2 times 10 to the 20 divided by the speed of light squared, and I get about 6,200 kilograms. So if you could turn 6,200 kilograms into energy, you could power the whole year. That'd be kind of handy. So just as a reminder, this is what we have so far, right? We have momentum, slightly different than the original momentum. We have the kinetic energy, gamma minus 1 mc squared. We have the rest energy of a particle, which is a whole new concept. It's mc squared. And the total energy, which you can write as either kinetic energy plus the rest energy, or you can write it as gamma mc squared. And you notice if you add these two together, you end up with gamma mc squared. So we can have some fun with that. Here's equivalent energy of a couple things. This is just for interest's sake here. We have an electron. It has a mass of about 9.11 times 10 to the minus 31 kilograms. Often it's written in, if I were to use mc squared to convert it to energy, it would be 8.19 times 10 to the minus 14 joules. There's a unit of energy that's really useful in particle physics and special relativity, and you may have seen it before. It's called an electron volt. All right, so 1 electron volt is the energy required to accelerate 1 electron, or is the energy gained by an electron when it's accelerated through 1 volt. And because of the charge in an electron, 1 electron volt ends up being equal to approximately 1.6 times 10 to the negative 19 joules. That's the conversion factor between electron volts and joules. And so for an electron, if you convert it to energy using E equals mc squared, and then you convert it to electron volts, it turns out that an electron has an energy of about 511 kilo electron volts. If you do it for a proton has an energy of about 938 mega electron volts. A uranium atom, 225 giga electron volts. So this is just to give you an idea of the energy equivalent of a few of these things. So I thought I would just do one of them real quick just to give you an idea. So the mass of an electron, again, is about 9.11 times 10 to the minus 31 kilograms, right? If I calculate the energy of an electron, the energy equivalent of an electron, mec squared, right, I end up about 8.19 times 10 to the minus 14 joules approximately. And if I want to convert it to electron volts, well, 1 electron volt is about 1.6 times 10 to the negative 19 joules. So that works out to about 511,000 electron volts, which we'll write in kilo electron volts. So 1 electron is about 511 kilo electron volts. So, and often so that would be the energy of an electron. So sometimes it's handy to express the mass of an electron so since EE is equal to MEC squared, you can write the mass of an electron as its energy divided by c squared. So sometimes we'll just leave that c squared, and if I plug this into here, I can say it's 511 kilo electron volts. Oops, my E is not working. There you go. Kilo electron volts per c squared. So sometimes instead of expressing the mass in kilograms or some other units, sometimes it's in electron volts per c squared. It's just another way of writing it. Okay, so and you can do the same with all the other tools there. So let's do some simple example here. So let's have a proton moving at 92% the speed of light, and let's calculate some properties for this proton moving at 90% the speed of light. Quick side note on here, right? The mass of a proton is about 1.67 times 10 to the minus 27 kilograms. So let's start by calculating gamma. Oh, and so we have the speed of this thing is 0.92 c, or beta is 0.92. So what's gamma? Well, gamma will be 1 over the square root of 1 minus beta squared. Right, so what does that work out to be? About 2.55, just to give you an idea. So let's find the momentum. So momentum P will be gamma mv, and when I plug in gamma is 2.55, m is 1.67 times 10 to the minus 27, v is 0.92 c, I get about 2.557 times 10 to the minus 2 kilogram meters per second. If I want to calculate the rest mass, right, that doesn't depend on the motion, right? That's just the mass of the proton times c squared. And if I were to convert it to MeVs, it works to about 938 MeV. If I wanted the kinetic energy, that would be gamma minus 1 times mc squared, right? So you would just take that 938 MeV and multiply times gamma minus 1. So this would be 1554 MeV. So look at that. Its rest mass is 938 MeV, but its kinetic energy is larger than its rest mass. There's more energy in its kinetic energy than its actual mass, and that's because it's moving at almost the speed of light. What is its total energy? Well, its total energy is just going to be kinetic energy plus the rest energy, or it's going to be gamma mc squared. You can calculate it either way, and you would get the same result. About 2392 MeV would be the total energy of this particle. So these are just some of the basic describing characteristics of a moving proton, right? What do we got next? Well, let's say that I have mass of an electron is there it is to high accuracy, right? 9.0938188 times 10 to the minus 31 kilograms. And I'm saying for a 100 MeV electron, find gamma and beta. So for this, it's to 3 significant figures, so we're going to use the speed of light is 299,792,458 meters per second. So when I say a 100 MeV electron, that usually means that its kinetic energy is 100 MeV. Okay? If I wanted to calculate its rest energy for this thing to high accuracy, right, and I would use the mass electron c squared, and I would plug in all the numbers. Now if I were to round it and keep it to a higher accuracy than usual, it would be 5.0997 kilo electron volts. That would be the rest energy of this thing. Okay, so we're told that the kinetic energy is 100. We're told that the rest mass is that, and now we're asked to find gamma and beta. Well, we know it's total kinetic energy, so we should be able to find gamma from that, because to find gamma, we're going to use that the kinetic energy is equal to mc squared times gamma minus 1, right? So solve for gamma, and we get that gamma is equal to the kinetic energy over mc squared plus 1. We know the kinetic energy is 100. We have a very accurate calculation of mc squared, and I can solve that for gamma. And that gives me 196.696 when I plug in all the numbers. And then I can get beta from gamma, right? Remember beta is the square root of 1 minus 1 over gamma squared. So I can get beta, and that works out to about 0.99997. So in other words, it's moving at 99.997% the speed of light. Weird stuff. So in this question here, it's just asking you to calculate the total energy, kinetic energy, and the rest mass for an electron at 5 different speeds. So I'm just going to make a little chart here. So let's say we have here, and we won't do the actual calculations, just sort of give you the results. So say at different betas, right? So when it's at rest, when it's moving at half the speed of light, when it's moving at 99% the speed of light, versus when it's moving at 99.9% the speed of light. Right? Well, for all of them, the rest mass is going to be the same, right? Because E naught is the same in all cases, right? We saw it before, 511 kiloelectron volts. Because that doesn't depend on how fast it's moving, that's just its rest mass. Its kinetic energy, of course, will be different for all of them. You would calculate it using this. When it's at rest, its kinetic energy is 0. It's moving at half the speed of light, it's 79 keV. When it's moving at 99% speed of light, it's 3,111 keV. When it's moving at 99.9% speed of light, so just like less than 1% faster, it's all the way up to 11,000 keV. So the total energy is just the sum of those two things, right? It's E naught plus K. So here its total energy is just its rest energy when it's at rest. Its total energy is going to be 511 plus 79, so that looks like it's about 590 keV. When it's moving at 99% speed of light, 3,111 plus 511, so it'll be 3,622 keV. And then when it's moving really fast, the rest mass is not a big part of the speed. So this is just giving you an idea of what the kinetic energy and the total energy is as you go faster and faster. So one last fun problem here. A pion is created with a total energy of 1.35 × 10⁵. So a pion is an exotic particle, and we'll learn more about that in a little bit. But it has some total energy here. So its total energy of the particle is 1.35 times 10⁵ MeV, and we're told that its rest energy is 139.6 MeV. Okay, so what we can do is, and we're told that in its rest frame, it decays at 35 nanoseconds. Its half-life is 35 nanoseconds. So its half-life in its rest frame is 35.0 nanoseconds. So what we're going to do is we want to find out how fast this pion's going. All we have is its total energy and its energy, but we can use that to find gamma and beta, and then we can use that to find out how long is this until this pion decays in our frame. Okay, so let's see. So to find gamma and beta, we're going to use that the total energy, remember it can be either kinetic plus this, or it can also be just gamma mc squared. So we're going to use this to solve for gamma. So gamma is equal to E total energy over mc squared. Remember, mc squared is the same as the rest mass, right? So I'm going to plug in 1.35 times 10 to the 5 MeV divided by 139.6 MeV, and I get a gamma of approximately 967. So that is a very large gamma. That's a factor of 1,000. And if I were to use that to solve for beta, right? Remember, I invert the equation, 1 minus 1 over gamma squared. I get that beta is about 0.9999. How many nines do I have there? I think it's 6 nines. I'll have too many. That's way too many. But sometimes you need a little extra for... so it's moving fast, right? That sucker is moving fast. We can use that then to find the half-life, because T half-life in a moving frame is going to be equal to gamma T half-life in its rest frame. So we can solve that, and we plug in for gamma, and we get about 338, approximately, I'm rounding here, nanoseconds. So it'll live a lot longer when it's going through that, right? Initially, its half-life in its own frame was 35 nanoseconds, but when it's moving fast enough, its half-life will be, in our frame, will be about 33,000 nanoseconds. So that's an introduction to energy in special relativity.